Hello everyone, and welcome to today's chem lesson. Today we're going to be continuing our talk of periodic trends, these patterns that we see across the periodic table that can be determined based on the position of atoms and the patterns that we've discussed already, like the shells and the valence electrons. Today we're going to be looking at electronegativity, which is a measure of an atom's ability to attract electrons. And now this is a little bit different from ionization energy. In ionization energy, we were looking at how much energy needed to be put in to remove a valence electron. With electronegativity, we're looking at how easy is it for the atom to add an electron. So this is opposite of ionization energy in two ways. One, we're looking at gaining an electron instead of losing an electron. And two, we're looking at an internal force for electronegativity as opposed to an external force. And to put that in a little bit plainer English, for ionization energy, we're saying how much energy do I need to spend to pull away the atom's electron. Right? So external, I'm doing something to the atom. But for electronegativity, it's saying how good is the atom at pulling in new electrons. Right? So it's internal, the atom is doing the pulling. Electronegativity is measured on a scale from 0 to 4, where 0 is the lowest and 4 is the highest. So something with an electronegativity of 4 is very good at taking in electrons, at pulling in new electrons. Something with an electronegativity of 0 is really, really bad at pulling in new electrons. And so the first thing that you might think about when you're thinking about what would make something have a high or a low electronegativity might be your valence electrons. Right? If I'm looking at two things and one has 2 valence electrons and one has 6 valence electrons, this element wants to lose 2 electrons. It does not want to gain any, right? It wants to get rid of the ones it has to go down to 0. So when we measure how good is it at taking in new electrons, it's going to be bad at taking in new electrons because it's not trying to take in any electrons. Meanwhile, on the other hand, something with 6 valence electrons is trying to gain 2. And so this would be something that has a higher electronegativity because it's trying to gain electrons. And so just like before, we're going to look at the 4 corners of the periodic table. We're going to look at lithium, fluorine, francium, and ununceptium. And we're going to take a peek at these 4 elements and see if we can figure out which way our trends are going to go for electronegativity. The first thing we want to think about, electronegativity is about gaining new electrons. Which of these elements wants to gain electrons? Lithium and francium, with 1 valence electron, they want to lose. But francium, fluorine, and ununceptium wants to gain. electrons. Right, one valence electron for lithium and francium means that their options are gain 7 or lose 1. And we know that an atom is going to take the less change, right? So instead of gaining 7, it's going to lose 1. So they want to lose their valence electrons, where here we have the opposite for francium, for fluorine and unseptium, where they have 7, and so they want to gain 1. And we can extrapolate, if these are our corners, the things in between want to lose until we hit the threshold where they want to gain. And so if we're going to put a trend on this, if we're going to put a line here, it's going to tell us which way does electronegativity increase. Where do atoms want electrons more? It's going to be an arrow that points from left to right. And as we go from left to right, the electronegativity, the desire of an atom to pull in more electrons, is going to increase. These on the right side have close to full valence shells. They want to gain electrons. These on the left side have almost empty valence shells. They want to lose electrons. But the periodic table doesn't just go from left to right or right to left. The periodic table also goes up and down, and we need to look at these columns and make comparisons within the column. Both fluorine and unseptium want to gain 1 electron. Electronegativity is a measure of how good an element is at gaining an electron. These two atoms are not the same. They are really different, but the one big difference between them is the number of shells that they have. Unseptium has 7 shells and 7 valence electrons. If it wants to pull in an electron, it is adding something to its already pretty full plate. It's juggling 7 different shells and trying to pull in a new electron. Compare that to fluorine, who has 2 shells to juggle and tries to pull in a valence electron. It's going to be easier for fluorine to get that electron than it is for unseptium. There are so many other electrons being managed in these 7 shells than there are for fluorine. So even though they both want to gain, fluorine will have an easier time gaining electrons because it has fewer shells. And so if we want to put the trend down for the columns, as you go up, electronegativity increases. As we look from left to right, the thing that factors in the most is the number of valence electrons. Right. More valence electrons means that the atom wants to gain which raises the electronegativity. Right, it's all about how badly does that atom want to pull in electrons. How good is that atom at pulling in electrons? For our groups, looking up and down the columns, the number of shells is what plays a big part. The more shells an atom has, makes it difficult to add more electrons. Right, having to juggle 7 shells and try to add another electron is a lot harder than juggling 2 shells and trying to add 1 electron. Right, those extra shells get in the way. There are other factors that are taken into account. So for electronegativity, those are our 2 big reasons. Number of valence electrons, the higher they are, the closer they are to 8, the more the atom wants to get to 8. And the fewer shells they have, the easier it is to grab an electron. The more shells they have, the harder it is to grab an electron. Now, with that in mind, if I told you that these 4 electronegativity values align to the 4 elements in our corners, could you put them in the correct spots? Can you assign these 4 electronegativity values to the correct elements? Looking at these 4 values, we know that the 2 smallest values should be assigned to the elements that do not at all want to gain electrons. That's going to mean that our 0.2 and our 1 should go to lithium and francium. These are the ones that do not at all want to gain electrons, which puts our 2.2 and our 4 to unseptium and fluorine. Right, these want to gain, they will have higher values. These want to lose, they will have lower values. Now, if I'm going to differentiate between these 2 that have the same number of valence electrons, then I'm going to look at the number of shells. I'm going to say the more shells, the harder it is to pull in electrons, which splits my 0.2 and my 1. And I'm going to do the same thing on the right side. Put my 2.2 and my 4. Because even though both of these atoms want to gain, unseptium has more shells, which is going to make it harder for that atom to pull in electrons. There's one more thing I want to mention before we transition away, and that is Table S. Now, Table S is on your reference table. It's a whole 2 pages of words and numbers. And what we have given to us on table S is a large portion of the elements, almost all the elements, and their ionization energies and their electronegativities, along with melting point, boiling points, and densities for the elements. But the most connected to what we were just talking about is our ionization energies and our electronegativities. They're here, they're listed for you. So if there's ever a time that a question says, what is the ionization energy of silicon? You can look that up. Silicon ionization energy, 787 kilojoules. What is the electronegativity of calcium? Something else you could look up, right? Where's calcium? There's calcium. Electronegativity for calcium is 1.0. Right? These are values that are not mysteries. They're not hidden information. They're here right on the reference table for you if it ever calls for a specific value. And with that, I'm going to transition us over to our Google Meet for questions, comments, attendance, announcements, and concerns. So I'll see you there.